from the Escola Politecnica of the University of São Paulo to present our... Hello, I am Arturo Forner-Cordero. I am here with Victor, Harman, and Camila Taira from the Escola Politecnica of the University of São Paulo to present our work about the design of a torque measurement unit for upper limb industrial exoskeletons.
So the exoskeletons, they are assistive devices along with robots. They are used for technical assistance to the human tasks in factories, for example. So in this work, we compared three of the most common and most used types of exoskeletons, three models. And our purpose was to benchmark the exoskeletons actuation to measure torque.
We studied three exoskeletons in order to see what would be the body size limits for a dummy. That dummy was developed using an average body size from workers inside a particular factory. We consider also the degrees of freedom that would be necessary to study those devices, and the required torque limits to develop the test bench. The control systems was also studied, and the data acquisition system is consistent with the requirements for that type of measurement. And the mechanical structure is studied in that paper, as well as the total test cycle time to perform the evaluation tests of each of the exoskeletons.
This work paves the way to the definition of standards based on objective measurement of the loads applied by the exoskeletons on the user. Okay, thank you everyone.
Lacerda, and I present you the article Physical Interaction Analysis of the Human Body Dorsal Region with a Robotic Manipulator that was written by me, Lucas Melo, Gustavo Lar, Professor Marcelo Becker, and Professor Glauco Caurin. The process of teaching a robot how to interact with humans is complex due to the fact that there is a lot of variables in the contact scenario that controllers need to deal with. Physical robot interaction researchers have been approaching this problem by looking for limit values for these variables, such as deformation and force, for each part of the human body. In this article, we focused on the human dorsal region, and we proposed the development of a virtual model for human dorsal in a virtual environment called Mujoko that will help the development of virtual experiments of contact between robot and this human body region. The development of this article followed some steps. The first one was the investigation of the dorsal anatomy. After this, similar structures of this region was grouped and optimized, reaching a number of 9 points able to represent the entire structure of the dorsal. On the left part of this screen, you can see a table representing the content that each point is representing. The second step was the development of the model inside the virtual environment Mujoko. All the behavior of the LBR EVA virtual model was controlled by the impedance controller, whose equation is shown on the screen. The result we obtained is shown on the screen now, and the third column is the values obtained from the evaluation using the equation we developed through our studies. The fourth column is the values of stiffness we obtained when is making the simulations in the Mujoko. Even though not achieving the exact reference numbers, good results in Mujoko were obtained, especially when we think about the behavior of the blocks that respect the behavior of the real dorsal human region. Thus, the model is said able to represent a real dorsal behavior when it's submitted to contacts. We would like to thank AWS, CNPq, FAPESP, CEPOF, and FINEP for helping us in the development of this article. Here the reference we used in our article, and thank you for your attention.
Hello everyone, myself Padmini Singh. The topic of my paper is Singularity free stabilizing controller for non-holonomic mobile robot using sliding manifold. The motivation behind the work is in various applications such as delivery, protection, maintenance, terrestrial observation, etc. Mobile robots are now becoming more relevant over the past couple of years. Many prior methods, in order to simplify the nature of a control rule, neglect second order model dynamics. Generally, they either show kinematic tracking or kinematic stabilization, but dynamic tracking and stabilization are still a wide area of research. So this is the main contribution of the paper. The paper proposes kinematic as well as dynamic stabilization of non-holonomic mobile robot using novel sliding surface. So this is the pictorial view of mobile robot, and equation 3 represents the kinematic model. Equation 4 represents the dynamic of the mobile robot. We have certain transformation. We have obtained equation 7 and equation 8, which gives the chain form of the kinematic as well as dynamic model of the mobile robot. So now our objective is to design U1 and U2 for both kinematic and dynamic model. For kinematic, U1 and U2 are velocities, and for dynamic, U1 and U2 are torques. So the novelty of the proposed work is we have designed novel sliding surface, which is given in the form of equation number 11a and 11b, and by using the virtual surface S3, because S1 and S2 are a combination of 3 variables. So for obtaining the Z1, Z2 and Z3 all goes to 0, we have to design a virtual surface which ensures the convergence of all the 3 states Z1, Z2 and Z3 in the reaching phase only. More detail is given in the paper. The kinematic control are given in equation number 17 and 17b, which are chattering free as well as singularity free. Likewise, by taking the double derivative of the sliding surface and putting all the variables, we are getting equation number 21a and 21b, which also ensures chattering free controller for dynamic model, and it is also free from singularity and chattering problem. So these are the simulation result for kinematic stabilization, and this is the simulation result for dynamic stabilization, and this is the comparative study with the existing method The conclusion and future scope is given. The paper proposes a singularity-free stabilizing controller for dynamic and kinematic model of mobile robot. The unique feature of the proposed method is normally sliding surface. Future scope of the present work is to stabilize the system in presence of singularity. These are the references. Thank you.
Good morning, everyone. My name is Aline da Conceição Mateus. I am a doctorate student at Aeronautics Institute of Technology, ITA, in Brazil. I would like to present an overview of our work, Washout Filter Parameterization of a Robotic Flight Simulator, done in collaboration with Emília Villani and Wesley Rodrigues de Oliveira. Robotic flight simulators have emerged as a low-cost alternative to conventional flight simulators. Despite enormous potential, theories have been conducted regarding the representativeness of movement of the simulator. Thus, we propose an optimization of the Washout filter using the genetic algorithm to obtain the perception during the plane's takeoff. Three configurations were proposed. Solution 1 that does not impose displacement limits for channel B of the simulator. Solution 2 with a limited displacement of 15 degrees for channel B. And solution 3 that considers the limit of 15 degrees and a different configuration of the cost function. It was found that the solution that maximizes pilot perception is the solution 1. Solutions 2 and 3 were similar, which indicates that it's the best configuration to be obtained with the current workspace limitation. The comparison of three solutions also indicates that the rail could be further explored to increase the sensation of acceleration during takeoff. The next phase of this study includes the realization of flights in SIVOR, making pilots evaluate the optimized and the previous washout filter configuration to determine the gain in relation to motion representativeness.
Hello everyone, I'm going to start the presentation of our paper that is called Redundant Robotic Kinematic Zero Analysis for Neurosurgical Procedures. So we are going to study a neurosurgical robot that helps in the placement of electrodes for stereoelectroencephalography. And moreover, we're going to talk about collaborative robots that are also redundant manipulators. So the motivation of our paper is to study and improve the redundant kinematics of these manipulators so that its accuracy is enhanced. The contribution of our paper is a method to analyze the kinematic accuracy of redundant robots and also certify that different configurations in the null space are capable of minimizing the error on the end effector. In order to achieve that, we used the 7th degree of freedom KUKA robot, and we studied its inverse kinematics. And moreover, we studied the relationship between the position error dx at the end of the robot and the error of the joint's position dk. We carry out simulations in MATLAB to explore the redundancy at the robot's final position. And here is a video of the redundant circle, and you can see here that the joints can articulate so that the manipulator moves its elbow according to the perimeter of the redundant circle without affecting the final position and orientation of the tool center point. Here are our results. So first is the plot of the Cartesian certainty or Cartesian error and the manipulability measure. And you can see here that we obtained different values of Cartesian uncertainty and manipulability measure for different angles in the redundant circle. So the maximum Cartesian uncertainty was obtained for the angle of 108 degrees and the minimum at the angle of 278 degrees of this around the redundant circle. So in conclusion, we calculated the inverse kinematics for a redundant robot by analyzing its redundant circle, and for the same end effector pose, we obtained different values of Euclidean errors due to distinct Jacobian matrices for each possible joint configuration. It's proposed for future work a complementary analysis of the error related to the Euler angles as well as other measures to be optimized. Here are our acknowledgements, our references. Thank you.
Hi, I am Mário Sassinelli Filho from UFES, and I'm here to present the short video corresponding to adaptive dynamic control of a multi-articulated robot in backward movements. The idea is to control this chain, this articulated chain composed by a tractor element that is the Pioneer 3 DX robot, pushing two trailers that are articulated between themselves and with the tractor element. The idea is to control the point in the back of the last trailer, characterized by the coordinates x sub c and y sub c, and orientation W2 of the last trailer, which are mapped to the first element, to the tractor element. And we consider two aspects. First one is to apply a kinematic controller to the last trailer, generating the reference velocities necessary to change, to move this point accordingly, and transfer to this reference velocity to the tractor element. And to do this, we consider the extended kinematics of the last trailer, supposing or admitting that it's the same kinematics of the tractor element because they are both non-holonomic platforms, And this extended kinematics considers a fictitious velocity in the y direction of the robot frame, which should be imposed to be zero at the end. The entire control structure is composed by the robot itself, decomposed in the dynamic model and kinematic model, and the controller, which is composed of three blocks. The first one is the kinematic controller applied to the last trailer, whose reference velocities are mapped to the dynamic model of the robot. In this dynamic controller, we also use an updating law to adjust the parameters. Here we have an example, an application, a simulated application in which we have a large error, and after turning on the adaptation law, we have the convergence of the errors to very small values. And here we have how the parameters are adjusted along the updating. Thank you very much for your patience. Visit us in YouTube and Instagram, acknowledging the support of our sponsors. Thank you very much for your attention.
Okay. Okay, thank you to everyone for your presentations and for being here ready to answer the questions from the audience. Now I open the session to have questions from the audience, and just a reminder that the Induscon papers can be with expansion and modification can be published in two important journals, such as the IEEE Transactions and Industrial Applications, and in a special issue of the journal Machines from MDPI. That's an open access journal that will offer a 20% discount for the publishing of these papers. Okay, so maybe it's now to start with questions. Maybe maybe someone wants to ask something to the first presenter. That was actually me. So,
if you allow, Arturo, I would like to ask a question.
Yes, please.
Maybe starting with the paper and the approach for your device, what was the reason to choose a step motor and not a servo, since it would be also a solution which would provide information and also possibility for current control, among other things?
Okay. In this case, the choice of a servo was to provide a precise positioning and in order to measure the corresponding torque. So it was not really needed to have a servo for this application. We wanted to have precise positions and to measure only the torque provided by the exoskeleton at that position. Well, actually, I recognize that using servo could give us other options of design, but in this case, we opted for a low-cost solution. Also, because we wanted to. I mean, it's the first. It was the first type of device designed for this purpose. We are looking for kind of standard, setting a standard in the evaluation of exoskeletons. So we don't want something that's very expensive and very complex. Actually, we were looking for something very straightforward, and we needed precise angles. So a step motor was a cheap and reasonable approach.
Okay, thank you. And maybe if I could make a second question, also on more on the paper than on the video. You show on table 2 of your paper some big differences between the setup time, maximum and minimum. This was not very clear for me. Do you have this exoskeleton in your lab that you are using to put on the machine, or what is really what do you mean with this setup times? Where do you have more than 30 minutes? If I don't misunderstood.
Okay. This is okay. This table refers to the time that is needed to place the exoskeleton on to make the robot wear the exoskeleton, adjust it, and then perform the measurements. Okay. So we measured a range of times. The problem is that at the end, we suffered from a pandemic disease, like we couldn't carry out all the experiments that we wanted to do. So at the end, we could not show the times for different types of exoskeletons because we have different exoskeletons to measure.
You have different exos in your lab, but that was not very clear.
Yes, the problem is that these experimental results with the different exoskeletons are not presented here because of the pandemic problem. And so what we did is just the general procedure to do measurements with one exoskeleton. How much does it take to do all this setup, calibration, and all this stuff? Okay.
Okay. Thank you.
Any more questions? No? Okay, maybe we can go to the second paper of the session that was named Physical Interaction Analysis of the Human Body Dorsal Region with a Robotic Manipulator. I think it was Christian presenting, right? Okay. Hello, Christian. Has anybody has a question about this work? Okay, then I would have some question. One first point is that
I think he's having some problems hearing us. Are you able to hear us, Christian? Some technical issues, probably.
Eu acho que ele não está conseguindo ouvir. Acho que ele vai sair e eu adiciono ele de novo.
Okay.
Okay. Maybe we can go to another paper while he... Christian, you cannot hear us? You cannot listen to us?
I'm communicating with him with the chat. It's a private chat, probably. Okay. Trying to connect once again.
Okay, and now, okay, then he's going to out and enter here. While he comes back, maybe we can ask a question to the third presentation from. Oh, Christian is back. So,
Okay.
can you hear us now?
I listen well.
Okay,
Yes.
Excellent. So we are asking some, preparing some question. My first question is that you presented here essentially simulation results, right? What is the validity?
problems again. The problem is always again. So I will try to change my hand and do again here and the
Okay, your sound is not working properly. So maybe we can try to solve it and then move on to the next presenter. I have some questions for you here. They are waiting for you. You don't think that you are getting away so easily, but maybe when you solve it, we come back, and maybe we should move on in order to keep.
No, I have a question.
Okay. Please. Hi, hello, Mario. Please.
I have assisted your video, Mrs. Padmini Singh, and a problem we have always you use sliding surfaces is the problem of shattering. I could see in your graphics this effect, even though you have presented on simulations. So I would ask you, how do you intend to deal with this problem? And also,
sir, there is lot of chaos. Sir, please, yes, please, sir, repeat your question.
My question is about chattering effect that is always present when you use sliding surface.
No, sir, no, sir.
In your graph, the presence of this effect. The question is, have you run this controller with any real robot? Because when you run a sliding mode control in real robots, the chattering effect is still worse than in simulation. So this is an issue that should be considered. And it's not so difficult to run real experiments because we have a lot of non-holonomic robots available. So
sir, actually, okay, I understood your question. You are asking how chattering is eliminated in a sliding mode control. I am right?
Okay.
Okay, is this the question? That how chattering is eliminated?
I would say not eliminated, but at the first time, how you have it in simulation, because as I understood, Professor Mario is wondering if the shattering in the simulations are really replicated.
No, it is not chattering, sir. It is showing the control effort in presence of disturbances. This is not chattering in the simulation. Chattering, because we have used power rate raging law. Power rate raging law is in the form of, suppose S is a variable, minus K, S power alpha, signum of S. Due to S power alpha with signum S, there is not chattering.
Show the graphic, please.
Okay.
We have to do it. Fernanda, can you show is in your presentation in your video, or you can
sir,
show?
I will show my PPT.
Okay. I am Arturo Forner-Cordero. I am here. Oh.
Sir, is it visible to you? My screen?
No. Yes.
Hello. Okay, so which figure? Which figure number?
The previous.
Second
this
one?
Yes.
This one, okay.
The last one, you can see.
Okay.
The last two. The last two figures.
Control input. Control input. Control input?
No, the last two graphs.
Rest 2 means figure 2 or figure?
The two graphs in the bottom part of this figure. Figure 2.
Control effort you are asking about, or last F, posture, or control input in original form or control input in chain form?
The last one is posture in XY plane.
Okay, no, sir. This is the graphic representation, posture in XY plane. Okay, this is, sir, we have plotted this. This is not chattering. This is XY, how from any initial position it is going to 0, 0. This graph is showing that. This is not chattering, always happens in control input. Because we are designing control input with our reaching law, obviously. So there is never chattering in the tracking. There is always chattering present in the control input, and our objective is to eliminate that chattering. And using power rate reaching law, we have eliminated that chattering. Means we have reduced it to a quite significant value. And if we use, in place of power rate reaching law, if we use K signum as directly, in place of power rate reaching law, you can see here. This is dynamic control law. This is kinematic control law. You can see minus K1 S1 power 0.5 signum of S1. If in place of minus of K1 S1 power 0.5 signum of S1, if you use minus of K1 signum of S1 only, then there will be chattering. Because of S1 power of 0.5, there is no chattering. Because we have changed the reaching law to a continuous function. You can see here. This is the kinematic control law U1 and U2.
Haven't you run this controller with a real robot?
Yes, sir, we can apply this. We have done lot of control. We have done lot of experiments by using sliding mode control input in our lab on Pioneer P3DX mobile robot, and this can be applied. And if you have designed, suppose minus K1 of signum S, if you have used this, then you can replace it by some saturation function, minus K1 of tan hyperbolic S1. You can replace that, because in existing literature, you can replace for practical application signum S by tan hyperbolic S1. For experimentation, you can go for it. And in this paper, we have used power rate reaching law, which is chattering free. Means it reduced chattering to a quite significant value.
Okay.
Okay. Thank you very much for the question and the answer. Is there any more questions about this work? Or are there any more questions about this work? Maybe we can continue, and eventually, I mean, if someone has another question later about any of the previous works, it is possible to come back, okay? And feel free to ask a question about any of the works here. I have a question about to Christian about the simulation of the back tissues, but I think it's not possible to. Can you talk, or is it still not possible? The sound is not working yet. Okay, then maybe we can proceed to.
First.
And now we can hear you. Yes.
Yes, my audio is very bad. Sometimes it's good, but I can try to answer the question.
No, it's not working. Sorry. I think it's not possible. Glauco, can you answer the questions about this work?
Yes, I can try. Yeah, no problem.
Okay.
Can help. Yep.
But just some clarification, some illumination about this work. First is as I saw, you presented essentially simulations, right? How did you validate the model, or how do you plan to validate the model?
Yes, there is. This is a first step in this direction. In some sense, we have some standards for forces and deformations that could be applied to people. And at this stage, we are concerned to have a model that's very close to the reality and verify if we are not going beyond these limits. Then, if we can guarantee that our model is accurate enough and that our control is not exceeding some standard limits, then we are, of course, trying to put some instruments or sensors in the person, and this will allow us to do experimental with human beings. Okay, but this is just a very initial phase where we are trying to verify and try to the readiness level of the technology, just checking if we are really getting what we are planning with our controllers.
Mm-hmm. I must confess that it was difficult to understand, because you used the paper, it was used the word dorsal to measure in the dorsal instead of back, or I don't know if actually when it's mentioned dorsal, it is meant simply the back of the person, right?
Yeah.
Okay. Also, I have another question. You opted for Mujoko, that is a perfect. Okay, I'm not questioning this choice. But did you consider the different simulation engines? I'm thinking of, let's say, on the compatibility with other simulation environments that allowed also musculoskeletal simulations, for instance, such as OpenSim or whatever.
That's the big trade-off. There are some engines where you have musculoskeletal models well established, and on the other side you have Mujoko that is very suitable for contact and a very good contact model. We have both in the lab, but the communication is still a problem. But I know what you mean. We made this first approach with a very good model for contact and collision, of course, and probably we need to go ahead. But the new versions of Mujoko, they also allow to work with elastic contact or deformations. This also gives a lot of new possibilities.
Okay, excellent. I have no more questions about this work. Does anybody else has a question? Anybody else uses some kind of a simulation, dynamic simulation engine that could comment something about it? No, none of them uses. Okay, maybe someone in the audience has something to say about simulation. No. Okay, so maybe we can continue and move to the presentation from Ricardo Godoy. Was it no? What was the fourth one? The robotic flight simulator from Aline. Hello, Aline. Does anybody has any question for Aline about the washout filter parameterization of a robotic flight simulator?
I would have a question for Aline, if you allow Arturo to be the first to ask.
Please, Glauco.
Okay, I was wondering, Aline, congratulations for your work. It's very nice. I was wondering, you are using human perception models that are transfer functions. You have 2 transfer functions for human perception models. Do you have any comments? Because transfer functions are linear systems, and human beings, biological systems are normally non-linear. Can you comment on this? How good are they? What is the state of the art in this subject? This is not my field of specialty. I was really curious about this.
Yeah, that's a good point, because when dealing with the human beings, it's, as you said, it can be very complicated, very tricky, and it is also a difficulty when doing this kind of work, because in literature there are many ways, for example, to measure how a person can feel a movement. So this approach, it's a simplified approach, and the advantage with using perception models, as I used, it's because it's more simple, but the representativeness of the movement can be also measured by other metrics, like the OMC test, objective tests, which is presented in the standards for aeronautics, and also the representativeness of the movement can be measured by the performance of the pilot. So in literature is not, how can I say, it's not well established the best way to measure the representativeness of the movement. So which are doing in CIVOR now is trying this this metric to adjust our washout filter, and testing, as I did in the paper, cost functions. And this work is what I'm doing in my PhD, and this paper is a part of this work. I don't know if I answered your question.
Oh, yes, thank you.
Yeah. And maybe, I don't know if it has some, how can I say, some intersection with the first 2 papers, because in the flight simulator, we do also study the human factors, and maybe I think with the works with Exoskeletons, we have also this problem, I mean, how the operator interacts with a robot, a machine. It's not the same problem, but there are also some human factors, how can I say, dealing with this situation.
Yes, actually, more than this work on exoskeletons, some work that we carried out on measuring the gaze of the pilots during some training, and the gaze where the eye was fixed during the trainings. And maybe it would be very interesting to study the vestibulo-ocular reflex during simulation of motion and different accelerations, because you have a model, the ortholith system, but I mean, there is a very important effect that is the vestibulo-ocular reflex that serves to fix the gaze in the presence of accelerations. And that could be very interesting. And also, I could mention also, we have we are working on how sleep deprivation affects performance in human factors. And I think that could be also another aspect, because we know that sleep deprivation affects posture control. It affects different types of motor control. So maybe there is something there that we could there is some interesting research there that merits a trip to San Jose dos Campos to make some experiments with these ideas. Really, definitively, that's an interesting part. And I think that, as I understand, you took simpler human perception models, so you don't to start with. I think that in the maybe a possible way to improve results is to consider some to suit this human perception to different types of humans under different conditions. Maybe. So I don't know. Maybe maybe this could merit some kind of further research.
Okay.
I have seen something about model to model human behavior using transfer functions in teleoperation of robots, something like that. And a problem is how robust your system is to the variations of these, the way the different people behaves. So of course, you have identified these transfer functions, getting a lot of observations. Would you talk something about this?
Yes, actually, there are many review works on human perception models, which I choose on my paper was one of them, which is employed in previous works. But as you said, it's difficult to model how someone can perceive emotion. And in the motion perception, it's even more complicated because it's three systems working together: the visual system, the vestibular system, and we also can feel motion by like vibration by our skin, let's say. So what we do in flight simulation, it's we use these perception models, and we also do tests with pilots evaluating our configuration. So as I said, there is not a consensus of the best metrics, and we also have the presence of several pilots evaluating our simulation in order to deal with this problem, because there are two difficulties in this case: that to model how someone perceives the motion, and also you have a variability between people about how someone perceives the motion. So one of the problems of these works, it's the metrics. The metrics we employed is too not precise. It's difficult to have a precise metric for the perception of motion, and we deal with that doing several tests, several experimental tests with pilots. I don't know if I answered the question of Mario and Arturo.
I understood that you did not identify the transfer function, the parameters of the transfer function, but collected
Yes,
from the literature, but tested with different pilots. How many pilots?
Yeah, actually, in this part of the work, it's a model-based analysis, and as you said, I took the vestibular model from previous works, and these transfer functions were measured. It's used in the literature for other works, but the washout parameterization that I presented on this paper will be further evaluated It's not yet presented on the work, but I will do it as part of my my research in ITA. Okay. Did I answer the question?
Okay.
Okay.
My curiosity is just how many pilots have tested.
Okay. Yeah, actually, it's complicated to find pilots, but I think it's a simulator for research, so that's not a need. How can I say? It's not fixed a quantity of pilots, but if you need a simulator to be qualified for pilot training, there is a standard ICAO that establishes how should be the tests you perform in order to qualify the simulator as a level D, as a representative flight simulator.
Okay.
Okay. No more questions? Well, you can ask afterwards. So maybe we can move on, and then we can come back to further questions for Christian. That seems that he has the camera disconnected because the sound is, we hope that the sound is better, but Glauco maybe can also ask some questions. Now we move to specific questions about the fifth presentation about a neurosurgery robot. Actually, this robot is intended for Parkinsonian patients, to implant an electrode in Parkinsonian patients. Ricardo?
Yeah, the electrodes that we talked about is to treat epilepsy. Is to study and diagnose epilepsy.
And are these type of surgeries where the person is awake and doing something, and then the surgery is taking place at the same time, or not? Or in this?
I think that in this case, no. No, yes, they are implanted and they can, after the surgery, be awake. Yes.
Okay. So my questions are more specific. About this, you presented kinematic error analysis for a controller. What is the, my question is, what is the time, the execution time of this, the controller that you propose, if you have an estimation, so it can be used safely in a surgery procedure?
Okay, so we didn't actually use the controller. It was just an analysis of the error. So we are willing to only make an analysis of the error, and the controller, and also, for example, choose a new space controller. It's going to be done in future works.
Okay, I thought that you were trying to use this to develop a controller, and I don't know if let's say the processing time already would impair an application or not for, let's say, real use applications.
Yeah. Yes, we really want to implement that in future works, but for now, and due to pandemics, the work was only an analysis and simulated analysis.
Okay, and one question that I'm very worried about, and maybe you can also give me some light. What are the accuracy values that are, let's say, recommended for neurosurgery, and what are the, let's say, errors, margin of errors that human surgeons have? How many millimeters, or how many? I don't know. micrometers. And how would it compare to the performance of a robot?
Yeah, so the manufacturer from the EVA says that its accuracy is around 0.1 millimeters, and this is quite valid to neurosurgical procedures. I don't know exactly how much is the average accuracy of a human, but so
the
your question.
requirements, Ricardo, if you allow, the requirements for epilepsy are around 4 millimeters. And if you go more precise, 1 millimeter, you can do some neurosurgery for other pathologies. But the main source of error is not the robot in this case, but the image, the navigation system. The 3D navigation system is the main source of errors.
If that is the main source of error, why working on the error from the robot arm?
Exactly, because you have this degree of freedom, you know. This is exactly the point. You can change the robot position, and you can play with it. You have more degrees of freedom. That's exactly the point. And to show that you're not compromising the process.
Okay, that's exactly what I wanted to reach. Maybe can you? I don't know if everybody followed this reasoning. Maybe you can explain it a little bit more in detail, because I think that's a very interesting point, and that's why I wanted to bring it out, to bring it to this.
To explain the about the redundancy of the robot.
To explain how you are taking or using the redundancy to improve accuracy, and how do you plan to use that to improve the whole process that is subject to other errors, other sources of error.
Okay, so as we are talking about a robot that has 7 degrees of freedom, it's a redundant robot, so we have more than one set of joints configurations that we can reach the same TCP position and orientation. So in our paper, we evaluated that as we can use different joint configurations, we can have different Jacobian matrices, and this way we can have we can minimize the error in the TCP, in the end effector, while keeping the orientation, the same position in orientation. And this way we can enhance the accuracy. So we explore this redundancy and this different set of joints configurations to reach the same TCP position.
Okay. Any further comments on this work? No questions from the audience either? No? Seems that the session is a little bit of a sunny afternoon. Okay, so maybe we can move to the next presentation. From we have the presenter here, Mario Sarcinelli Figlio. Glauco, do you have any question for Mario?
Unmute your microphone.
Thank you. A pleasure to have you here, Mario. I was wondering, in this control approach, what are the limits that you are experiencing regarding the current position, at least the starting position, and the desired one? Especially if you look at the videos that you provide, At the starting position, you have the robot quite aligned with the desired trajectory. Is there any limit that you could exceed, or is it not a big issue? Do you need some trajectory planning before your position controller? Could you comment on this?
Yes, the idea is when you have a large angle between two elements of the chain, for example, the two trailers, 90 degrees, it is a situation named in Portuguese canivete, in English jackknife. In this situation, you have the effort from the first element to the second is orthogonal. So you can't move the second element in the direction you want. That is the limit. The angles θ1 and θ2 should not exceed these values. We are working specifically on this topic to avoid jackknife in a paper we have submitted to the Brazilian Congress of Mechanical Engineering, working on adjusting the gains of the controllers just to reduce this variation of the angles, so to avoid this. And you consider that it's more difficult when you have, for example, two trailers and one tractor element. When you use the tractor element plus one trailer, it's easier. The risk is much lower of this kind of accidents. But in this case, we have tested using the lemniscate curve because it demands more from the controller, because you have positions of high velocity and positions of high curvature. So you have to reduce the velocity in this case. And you have, this is the second stage of a study that now has three stages. The first one was to combine a kinematic controller with a dynamic one to compensate for the dynamic of the system, because we have identified a dynamic model for the tractor element, but not for the entire chain. Because if you use this kind of vehicle, for example, one of applications we have in mind in agriculture, to transport inputs or the harvest, you have load variation. So it's not possible to have a fixed dynamic model. So the idea of this paper is exactly to take this in account using an adaptive law. That is what we implemented in this case, adaptation. And for this kind of application, the best way is not to follow a trajectory. Instead, to follow a path, because along the path, you can establish your velocity. You are not dependent of the velocity of the trajectory. So we are looking for applications in which we can decide the velocity, such as in agriculture, even for parking a big truck with one or two trailers. This is why we emphasize the backward movement. In this video, you would see the tractor element is pushing two trailers. It's the same situation when a big truck is parking in the backward direction. So this is the risky situation. So the proposal of using the adaptive control is exactly to compensate for load variations and non-modal dynamics, because we identified the dynamic parameters for the robot, the tractor element, but not for the other elements, because these dynamics can change with diverse kinds of loads and diverse amounts of loads. So the idea is to compensate using the adaptive law. And you could see in the video that the parameters effectively changes very specifically along the navigation.
Maybe regarding the video, it seems at the beginning of the trajectory, or the movement at least, there's some a forward movement. Can you explain or comment on this behavior?
Because the path is oriented. We have selected some difficult positions. One example, I don't know if this is in this paper, but it is in the first paper we have published in an international conference, we have the situation in which the point of interest for control, that is in the middle of the back of the left trailer, is over the path, but the tractor element is behind. So you have to maneuver to point the tractor element in the right direction, because you have to follow the path in one sense, another in any sense. There is a specified sense of movement, a direction of movement. That is why the initial maneuver is quite complicated.
Thank you.
To complement, you should position put the point of interest over the path with the tractor element in the desired or in the correct direction. That is the problem for this initial behavior.
Okay, more questions? I would like to know, we have two papers that had a kind of similarities, or at least in the application. Maybe you can comment on the controller, maybe Professor Singh, she presented a controller for a autonomous robot, while Professor Mario Sarcinelli is presenting, let's say, the control of the backwards movement of a convoy of vehicles. Is it possible, or has any interest to use the controller proposed from Professor Singh to the problem addressed by Professor Mario? So to control a multi-articulated backward motion?
Yes, we are now thinking. We have not started applying this technique, but is to use the sliding mode control technique to compensate for any variation, no model dynamic or parameter variation. Because if you have, we can see a mismodeled dynamic, you cannot compensate just varying the parameters. So the sliding mode option is effective. We have used the sliding mode control for UAVs, transporting a bar, two UAVs transporting a bar. We have used this adaptive law, and also we are now with some experiments in using sliding mode. The idea is it's possible. There is no problem. Okay, there is no any previous conditions. The idea is exactly to test and to compare using the two approaches, different approaches. For now, we are going to experiment this approach using using adaptive controller, because we are in a particular situation, not only because of the pandemic, but also because the building where my lab is installed is under repair about 1 year. So we could not do any experiment with this system. We had done previous experiments, which are now being published in the Journal of Intelligent and Robotic Systems. They are editing the final version, and we had done these experiments showing that it's interesting to have a dynamic compensator associated to the kinematic controller. This is a final decision for us. We are using what we call nested loops or inner-outer control system. So our idea is exactly to combine kinematic control to move the vehicle and dynamic compensation to compensate velocity tracking error. because you know that the commanded velocity is not instantaneously assumed by the vehicle. You need to accelerate. So the dynamics is important in this sense. So we have decided to do this. How to deal with the dynamics? Now we are using adaptive control, and we are going to test with sliding mode control.
Okay.
A third option is to use a null space control to associate the supervision, let's talk in this way, of the two angles, θ1 and θ2, of the axis, of the connected elements. Okay.
Sir, there is one advanced sliding mode control. I hope you have heard about it, super twisting reaching law in a sliding mode. So super twisting has characteristic of it reduces the chattering as well as it rejects the disturbance. So it is and it can be directly applied with the first order system. And if you have second order system, you can go for continuous twisting. So there are a lot of advancement has been done in sliding mode control theory, and nowadays chattering is not a big issue in sliding mode. So
nowadays you have solutions to minimize. We are experiencing this using this technique in association with UAVs.
Yes.
We have solutions to minimize the chattering effect. Even though in UAVs, this is not so meaningful because it's almost not perceivable, the chattering, because of the velocity of the propellers. In this kind of a composite vehicle, maybe it's more important. We do not have these results today. We are thinking on starting analyzing this possibility.
Have you designed conventional sliding mode controller? Means through designing sliding surface. After that, you have means first step. Have you designed a sliding surface and then you have designed a sliding mode controller for UAVs or some for advanced UAV technique?
No, we have used it for UAVs till now.
Okay.
This has been interesting. We are about writing a paper.
Okay.
Paper.
I have also one paper on UAV on quadrotor perching. For perching application, I have one paper in System Journal. So there I have used second order reaching law. It is also chattering free. We did it in our lab on crazy fly quadrotor. And one back stepping controller we have designed using advanced sliding mode technique, because using the concept of back stepping and sliding mode, we have merged that controller, and the results are coming quite good, and we are planning to contribute something in the field of sliding mode and robust controller for UAVs also. So
okay, so we are now reaching the end of the session. I mean, if do you have any more comments about this, or maybe we can leave some time to Christian, that was not able to speak before, to say something. Christian, are you there? Can you want to comment on the questions that we made to your work?
Oh, yes. Can you hear me now, Professor?
Yes, now we can hear you, finally.
Thank you. I would like to apologize due to my connection. I don't know why it happened today in the morning. It was perfect, but now it happened. So sorry for this. Professor, could you repeat the question, please? Because unfortunately, I lost my connection exactly in the moment Professor Caurin was explaining. So I can put more comments on.
The question was related to the validity of the model and how do you plan to validate it if you plan to do some experimental work, or and how do you take the parameters to for this model. We already know why we chose, why you opted for Mujoko instead of other, let's say, options that would look, let's say, easier in some way. But okay, that's maybe you can elaborate a little bit on that question that was about the validity of the model. And another point that was not mentioned before was about the human perception, how it is, if it's related, the load is related also to the pain or levels of pain or discomfort of the user.
Okay, so the first part of the question, yes, in the future studies, I will prepare some real experiments to validate the model. This time I couldn't do this because we had some problems with the software of EVA, and we needed some time to receive from KUKA the new software to install again and repair the problem. So due to this fact, I needed to develop all the physics analysis in Mujoko. But Mujoko is a very accurate physics engine, and I talked about this in my article using two articles from Emil Todorov and his team, analyzing the accuracy of Mujoko and comparing Mujoko with other physics engines like OpenSV and Hapix and others that was described in their article. So due to this accuracy and the behavior of physics simulation inside Mujoko, I achieved good results, even though not developing real experiments. These results showed some behaviors, very similar that the behaviors the developers or the researchers of the article I used as a base for my measurements had in their studies. So due to this, I took my simulation as representing the real behavior. But of course, in the future, I will develop some real experiments. About the other part of the question, how the human and behavior and robot interact, how the robot know how to answer the interaction with the human, and how was the measurement that I used to develop the model. In this work, in this article I used it as a base, they collected 50 points of the back part of human body from the neck to the knee. I focused on the part of the back, and using this point, they developed a normalized curve showing the variation through the back of the human region, how the stiffness varies in this structure. So I took this normalized curve. I needed to make some math manipulations to express exactly the stiffness I wanted to present in my article, because they used a different approach to show this stiffness. So using this, I could demonstrate a linear approach for the stiffness, and I constructed also another normalized curve expressing this concept of stiffness. I use it varying through the back region of the human body. So the measurement they used was pain. I think was pain, but not a hard pain, if I can say like this. But the moment where the measure equipment of measure they used touched the skin and started the people that was in the experiment started feeling this not comfortable anymore. So when they stay, when the people in the experiment felt this, they stopped and collected the stiffness of that point. So it's pain, but not very hard pain, only uncomfortable zone, if I can say, in this way. Did I answer your question, Professor?
Completely, perfectly. I think that this is has been quite an extensive answer. So maybe it's about time to end this session. Okay. We presented here different, I'm kind of wrapping up. We presented here different applications of robot systems. Some are more related to control, other closer to simulation. Some of them are closer to, or let's say higher in a technological readiness level. So some are still a little bit far from real applications, but I mean, at the end, I think that we presented interesting results here. If anyone wants to make some kind of closing remark just before ending up this session, that has to, we have to finish on time because there's a session following afterwards. Please do not forget that your work, your valuable work, can also be submitted to one of the journals that are agreed with the conference to publish part of the selected works published here. Of course, they have to be expanded to become expanded or changed because they have to become, let's say, journal papers. That is a little bit different from a conference paper. Okay?
Okay.
So.
Nice to meet you again.
Yeah, nice to meet you too.
Meet.
Yeah, yes, nice to meet you too.
Maybe next time.
And maybe next time you know from Singh that probably she doesn't know. Professor Mario is in a very nice city by the sea.
Yes, but I am not encouraged to organize any other conference.
Okay,
I am okay. I organize
not only
3 or 4. It's enough for me.
There is not only a beautiful.
The youngest colleagues should have this now.
Okay.
I can participate, just enjoying, not organizing.
But you know, there is not only a magnificent beach, beaches there, but there is also a chocolate factory.
Yes.
Very close. So it is worth in several aspects.
Very good strawberries also. Very good coffee also.
Okay. Yes, true. That's true. Okay. So thank you very much to all of you for participating in this session. I hope that everything has been interesting. We've seen different aspects of robotics, from mobile robots to exoskeletons to flight simulators, neurosurgery devices, systems to measure simulations of the skin impedance. So I think it's it has been very, very nice to have all these, let's say, different perspectives from robotics here. So thank you very much, and hope to meet you soon in a different conference, or maybe some from here, some collaboration emerges in some aspects. Okay.
I will be here tomorrow for 2 sessions.
Okay. See you again, and goodbye. I don't know what time is. Where are you seeing? In which place?
Myself, Padmini Singh.
What?
It is 1 a.m. of 18 August.
Okay.
No.
It's very late. Yeah. So thank you very much for this.
Thank you. I really enjoyed.
Okay. Bye-bye.
Bye-bye.
Bye-bye. Thank you, sir.
Bye-bye.